Hello students, now we'll discuss the important that nature of a gas, that is ideal and real gas. On the basis of its nature, gas is generally two types, ideal gas and real gas. Ideal gas already we have discussed. If you obey the gas laws under all condition of temperature and pressure, that is ideal gas. But actually no gas is 100% ideal. Under certain conditions the ideal behavior deviates and shows that non-ideal nature, that is real gas. We can say that is real gas. So ideal gas means obey ideal gas equation, that we know that PV is equal to nRT. This is the mathematical equation of ideal gas equation, that is called equation for ideal gas. But if you divide that PV upon nRT, that is always 1. This is for ideal gas. This is for ideal gas. And this ratio is called Z. This ratio is called Z. Z is called compressibility factor. It is called compressibility factor. Compressibility factor Z equal to 1 means it is the ideal gas. But we know ideal gas, there is no force of attraction between the ideal gas. There is no force of attraction between ideal gas. Gas cannot be liquefied. This is the condition of ideal gas, because it cannot attract each other. But this is the hypothetical thing. Z is equal to 1 means that is a ideal gas equation. Compressibility factor is 1. But if you draw a graph, that this is the graph, this is for ideal gas equation, PV versus P. PV versus P. PV versus P, that is, this is your ideal gas. But it is observed, some gases like helium and hydrogen. Helium gas graph will be like this. This is for helium and this is for hydrogen. And if you see other gases, that is carbon monoxide, this is for carbon monoxide, and this is for methane. If you see, this is methane. The graph is like this. This, if you see, these 4 graphs just coming above the ideal gas graph. It is coming above the ideal gas graph. Helium, hydrogen, methane and carbon monoxide coming above the ideal gas. But that means, if you see the graph, these gases deviates from ideal behavior. When they are coming above the graph, this is ideal gas. If they are coming above the graph, that is called positive deviation. And that positive deviation means here Z value, you will see Z value will be greater than 1. That is called positive deviation. A positive deviation means gas generally incompressible. That gas is incompressible. Almost incompressible. But the graph which is coming below this part, if you see, this is the part up to this at a low pressure. At low pressure, that is graph is just coming below the ideal gas, that is negative deviation, Z value less than 1. Z equal to 1, this is Z equal to 1. Above this Z greater than 1, that is called positive deviation, that means almost incompressible. And here below, that is negative deviation, that is less than negative deviation, that means highly compressible. Highly compressible. This is very important terms, Z value, compressibility factor. But ideal gas, this volume, and if it is deviates from ideal behavior, that volume is called real. That means experimental value and your calculated value are different. And this Z also expressed as volume of which one? Volume of the we can write this is the volume of real gas. Real gas means does not obey ideal behavior, experimental value, and this is ideal volume. Ideal volume and real volume. Real volume means observed value. This is the observed value. This is observed value, and this is calculated. This ratio also gives the value of Z. Observed means experimentally. This is your calculated. So this is the relation between compressibility factor Z. Z greater than 1 means positive deviation, Z less than 1 means below the graph, that is negative deviation. If Z value is less than 1, that means the gas is highly compressible. This is very important, you have to remember this thing. Right. But it is being observed that PV is equal to nRT. This is for ideal gas. This is for ideal gas. But it is observed at very high pressure. At high pressure, when pressure is very high, at high pressure, the gas comes closer, then it deviates. It deviates from ideal behavior. It deviates from ideal behavior at high pressure. When the pressure is very high, then gas molecule come closer, then it attracts each other. That's why gas can be converted to liquid form. So, at high pressure, the gas deviates from ideal. High pressure and low volume. High pressure means automatically volume is low. High pressure, low volume, it deviates from ideal gas behavior. Okay? So, this equation PV nRT is corrected by Vander Waal. This equation, ideal gas equation corrected by Vander Waal. Corrected by Vander Waal. This equation is called Vander Waals gas equation or real gas equation. This correct equation is like this. As P is the pressure, that is observed pressure, that is calculated pressure, and the observed pressure should be greater than the calculated. That means P plus A n square by V square. Now the correction in pressure is Vander Waals done in, he has made some correction in the ideal gas equation. The pressure correction is P plus A n square by V square. I will discuss later. And the volume correction is V minus NB. Then is equal to nRT. This equation is called Vander Waals gas equation or real gas equation. It is also called a real gas equation. This equation is called a real gas equation. So that means the observed data and the experimental data totally different. Calculated and observed totally different. The pressure as per the ideal gas, there is no force to attraction. If there is no force to attraction, pressure should be very high. That's why he added some pressure term, A n square V square. This is the pressure term. And as the volume of gas very negligible, can be neglected in comparison total volume of gas. So that's why he neglected the volume, this volume, non-compressible volume of the actual volume of the gas from the total volume. So as there is no force to attraction, pressure will be more. As the volume can be neglected, that's why the volume value is neglecting from the total volume. So volume is corrected and pressure is corrected by the Vander Waals. So in pressure term, some pressure term is added. In volume, some volume is deducted. This volume is called non-compressible volume, which cannot be compressed more. That is called NB. What is N? N is the number of moles. What is A? A and B called Vander Waals gas constant. And this depends upon nature of the gas. It depends upon nature of gas. A depends upon attraction. If attraction is more, then A value is more. And B depends upon size. As the volume term, so it depends upon size. A is added with A is added with P. That means attraction. If attraction is more, then that Vander Waals constant is more. If size is more, then volume is more. So this is regarding A, B, Vander Waals gas constant. It depends upon the nature of gas. And this A n square V square term is calculated as the pressure is, as the force is directly proportional to number of gas molecules for unit volume. If number of gas molecules just around the gas molecule is more, then attraction will be more, then pressure will be also, this pressure term will be also decreased. So P plus A n square V square. A n square means number of gas molecules per unit volume. Number of gas molecules per unit volume is more, means attraction is more. That's why A n square V square term is added. And B is the smallest volume, taking B generally is equal to 4V. B is the non-compressible volume, that is equivalent to 4 volume spheres. 4 gas molecules having volume is V. Gas molecule considered as spherical body, volume is V, so V equal to 4V. N is multiplied means number of moles of gas. So B is equal to 4V, you remember. So this is the pressure correction and volume correction made by the Vander Waals. That's the ideal gas equation is corrected in the form of P plus N square V square into V minus NV into nRT. In volume, the some non-compressible factor is deducted, and the pressure, some, as there is no force of attraction, that's the pressure will be more. That's why he added some corrected pressure A n square by V square. So what is the unit? One unit of A and B. As P is equal to A n square by V square, that means this term is pressure term. This is totally pressure. So P is equal to N square V square implies A is equal to P V square. P V square by N square. So what is the unit of A? That is ATM. V liter square upon per mole square. So P is the ATM, V is the liter square, and N square means mole minus 2 per mole square. This is the per unit of A. Then what is the unit of B? B is equal to volume. So V is equal to NB as per the unit. So implies B is equal to V by N. V means liter per mole. If the volume is more, if the volume of gas is more, then V is more. What is A? A depends upon liter atmosphere, liter square atmosphere and or mole square. That means if the attraction is more, then A will be more. So this is regarding the unity of A. That means A, B are Vander Waals gas constant. These are called dimensional constant. It has units. Okay. Then very important thing is that how these two factors related to this. If pressure is low, at a low pressure, when pressure is low, this Z value will be 1 minus A by RTV. This is the derivation you can derive from this. From where? From Vander Waals gas constant taking the low pressure. At low pressure, Z is equal to 1 minus A by RT by V. What is this? That indicates Z is less than 1. That means at low pressure, Z is less than 1. When pressure is low, the Z value will be low. This condition. But at high pressure, when pressure is very high, Z is equal to 1 plus. What will be the calculation? You will calculate this one. 1 plus PB by RT. 1 plus PB by RT. That means here Z greater than 1. When pressure will be very high, Z value will be greater than 1. Greater than 1 means that is towards positive deviation. When at pressure is low, that is Z equal to Z less than 1. That means negative deviation. So this is the some important relation regarding low pressure and at high pressure. And so this equation that is related to low, that is moderate pressure. We can say that is not low, that is moderate pressure. At moderate pressure, that Z is less than 1. But at very low pressure, that Z equal to 1. If we apply this, if pressure is very low, then volume will be very high. So this is regarding the relation between Z value. Then another important thing is the gas can be liquefied at high pressure. When pressure is very high, gas will be liquefied. But it has been observed that some gases will not be liquefied still by increasing pressure, will not be liquefied. So the liquefaction of gas may be done at a particular temperature. You have to maintain that temperature to liquefy the gas. This temperature is called critical temperature. This is called critical temperature. Critical temperature, temperature above which gas cannot be liquefied. Above which gas cannot be liquefied. Above which gas cannot be liquefied. So that is a fixed temperature above which gas cannot be liquefied. So that you have to bring the temperature below that temperature. Then by changing the pressure you can liquefy the gas. So this is called critical temperature. Symbol denoted by TC. That is critical temperature. So critical temperature, if critical temperature is very high, gas cannot be easily liquefied. For example, that ammonia gas has a high critical temperature than nitrogen. Critical temperature of ammonia is very high, so that easily liquefied. If the gas temperature is above critical temperature, if critical temperature is very high critical temperature, so gas can be easily liquefied. If critical temperature is low, so very difficult to liquefy. For example, we compare to hydrogen, very low critical temperature hydrogen, the critical temperature is very low, so that's a very difficult to liquefy. Hydrogen, methane, neon, like this. Hydrogen, then we can say neon. Neon also cannot be easily liquefied. So like this. So these are the critical, the high critical temperature means can be easily liquefied. Liquefaction will be faster. This is the liquefaction. Ammonia is liquefied, then nitrogen, hydrogen, neon, like this. So this is regarding critical temperature. So the volume at which gas is liquefied, that is called critical volume. So there is a critical temperature Tc, similarly Tv critical volume and Tp critical pressure. So critical temperature Tc, critical temperature, then Vc, this is called Vc critical volume, and this is Pc, this is Pc critical what? Critical temperature, critical pressure and critical volume. These three are interrelated, and for a particular gas, at what is the critical volume, what is the critical pressure, what is the critical temperature required for the liquefaction of gas. So these three factors also related to Vander Waal's gas constant. How? It is calculated that Vc is equal to 3B. You have to remember this for calculation. Vc is equal to 3B. Vc is equal to 3B. And Tc is equal to Tc. Tc is equal to 8A by 27 RB. This is our Tc, critical temperature. That is, what is this? 8A upon 27 RB. Then Pc is equal to A by 27 V square. A by 27 V square. So Vc, this relation is important. To remember this for problem for calculation. Vc is equal to 3B, Tc is equal to 8A by 27 RB, Pc is equal to A by 27 V square. You have to remember like this. Here Pc 27 is in denominator. So each A by 27 RB, A by 27 V square. Calculation part is not required. Directly remember Vc is equal to 3B, Tc is equal to 8A by 27 RB, Pc is equal to A by 27 V square. So this is the relation between critical volume, critical temperature and critical pressure. So this is the relation between critical temperature, pressure and volume. And what is the mainly what is the critical temperature? Critical temperature, the temperature above which gas cannot be liquefied. To liquefy the gas, you have to bring the temperature of the below the critical temperature. Then gas can be liquefied. If it will remain above that temperature, it cannot be liquefied even if by increasing pressure. So this is relation between this, very important. One thing is high critical temperature means liquefaction will be easy. Critical temperature is very high means gas can be easily liquefied. You note down this point. High critical temperature, gas will be easily liquefied. This is very important. And if at low pressure, when the pressure is very low, then volume is very high. At high volume, what happens? There is no force what attraction to the gas molecule, Z equal to 1, that is ideal behavior. Ideal nature. So at very low pressure, Z equal to 1. But at moderate pressure, Z is less than 1. But at a very high pressure, Z is greater than 1. This is a very important relation between compression factor and the nature of gas related to the and here also related to A, B also. Here you see that if B is very high, B means volume. If that non-compressible volume, if non-compressible volume B is very high, then what happens? This will result to what? That low critical temperature. So this is the regarding some calculation. So regarding critical temperature, pressure and volume. So this is regarding ideal and non-ideal gas. Ideal gas mainly obey all gas laws. If you draw a graph between PV and P, it will be a straight line. If graph is not coming in straight line, means that deviating from ideal wave, generally deviation takes place at high pressure. When the pressure will be very high, the volume will be very low. In that condition, they starts attraction one another. Then gas will be attract each other, so deviates from ideal wave. Ideal wave means there is no force for attraction. That's why really the gas does not 100% ideal. Under certain conditions, the ideal wave is more. That's why this Vander Waal corrected the ideal equation into P plus n square V square into V minus Nv is equal to nRT. N is the number of moles. This is the corrected equation by Vander Waal. It is called also real gas equation. This equation obeyed by all gas, all conditions. So it is, you can say it is a real gas. Real gas. Actually, no gas is 100% ideal. So this equation used for all types of gas, we can utilize this equation. And that the significance of A, B already we have discussed. So this is regarding what? The ideal and non-ideal gas. You practice more. Any doubt, you can ask. Okay? Thank you all.